Good morning, good evening, good afternoon. It's time for us to start chapter 3. Now, in chapter 3, we're going to be talking about how we deal with vectors. In chapter 1, we kind of mentioned vectors. We kind of looked at some 2D things, but we quickly went into chapter 2 where we were all one-dimensional. As we approach chapter 4, we're going to be in 2 dimensions. And as we go to 2 dimensions, we have to move to vectors, and vectors in 2 dimensions. So just some handy-dandy reminders. Remember, a vector is anything that has both magnitude and direction. A scalar only has magnitude. Velocity is a vector. Speed is a scalar. Displacement is a vector. Distance traveled is a scalar. If we look at the image here on the screen, okay, you can see that if we look at the pathway followed by our individual who walked from the house, okay, they followed this serpentine-like pathway. And that would be their distance traveled. But their displacement is 200 feet, which is the straight line distance from where they started to where they ended, okay? So their distance traveled is actually longer than their displacement. Will have a greater magnitude. All right, now, let's think about the properties of vectors. Okay? Give us some more light. 2 vectors are equal if they have the same magnitude, length, and direction, relative angle to a parallel axis, even if the 2 vectors do not have the same starting point. So let me show you an example. We're going to draw over here on the whiteboard. Okay? So there's the whiteboard, so I can draw. So if I had a vector A, okay, and it started right here, and it went right here, vector A. If I had a vector, okay, and it's sitting on this axis. If I were to draw another axis here that's parallel to the first, and I draw a vector at the same angle and the same length, okay, vector B. Vector A equals vector B if the magnitude of A equals the magnitude of B, and this angle theta and this angle theta 1 are equal to each other. Okay? These axes, these 2 x-axes, these 2 y-axes are parallel. So when we say that 2 vectors are equal, that's what we're talking about. Now, let's turn back to the front screen, and let's talk about adding vectors. Okay? If we add 2 vectors, a vector C equals A plus B and B plus A. When we're adding vectors, it doesn't matter which order we add them in. Okay? Now, let's look at things graphically. How we add vectors graphically. All right, let's scroll down here a little. And I'm going to blow up things just a little. Now, if we looked at vector E plus D, we know to graphically add them, what we want to do is take vector E and slide it up to the point or tip of vector D. And then to add, graphically, we connect the tail of D to the tip of A. Now, let me slide over here again so that I can draw it for you. Okay? Let's draw. So, if this is vector D, and this is vector E, I know they're not exactly the same. I would just take this vector, slide it up here, redraw it, okay? And the sum of those two will go from here to there. I'll call it vector C. Now, what I want you to notice is if I took D and I slid it up to the tip of E, okay? I could redraw D there, just like I redrew E over here. And notice I get a parallelogram. So no matter if I add E plus D, or D plus E, or E plus D, I get the same vector C out of the addition. All right? Now, just so that you have a prettier view, let's look over here at the computer screen. Okay? A demonstration of the tip to tail method. So you can say D plus E gives me the vector F. And they call that tip to tail. So we slid the tail of vector of E up to the tip of vector D. Okay? Now, let's look at problem 3.1 on page 73 in your textbook. Here we've got three vectors, vector A1, A2, and A3. The problem asks us which one, A, B, C, D, or E, is the sum of those three vectors. Now guys, if you look at adding vector A1 and A3, if I take A1 and I slide it down to the tip of A3, I get a sum vector that only points down to about there. Actually, that's probably a little far. Probably needs to be right about there. Okay? So if I take these two vectors and I add them together, so I take this one and I slide it over here, then I'm going to get a vector essentially pointing straight down. So the sum of these vectors is C. Now let me draw it just so that you see what I'm doing. Okay? So I've got A1, A3, and A2. So if I take A1 and I take it down here to the tip of A3, okay, that's A1 moved, then the sum of those two vectors is just a vector here. And if I take this vector and add it together, just move this down to here, and this is the total sum vector. All right? So, the tip to tail method. Now, let's get back on the main screen. All right. When you multiply a vector by a scalar, all you do is you change the length of a vector. So if I have vector A and I multiply it by a constant C, I get a vector B that's going to point in the exact same direction as vector A. It's just going to be longer. Okay? If you multiply a vector by a -1, all you do is reverse the direction of the vector. So, if you look at vector A and vector -A, they point in opposite directions. Something to remember is that when I have a vector A plus a vector -A, they always add up to 0. Okay? You always are back to where you started from. You get a 0 magnitude vector. Okay. Now, when we do vector subtraction, so if I had vectors Q and P here, and I wanted to take P minus Q, think about taking Q up to the tip of P, okay, and then reversing the direction. So let me show you the images here. So vector r is q plus or minus p. So if I drove q in that way, now I've drawn q in the opposite direction. It has the same magnitude as q. The original q just points in the opposite direction. And there's p plus or minus q, or p minus q. Whereas when we're doing addition, it doesn't matter which order we add in. When we're doing subtraction, it does. Okay? Q minus p will not equal p minus q. All right. Let's keep moving down. Now, the graphical method for adding and subtracting vectors requires some very careful measurements of angles and lengths. It's very easy to make a mistake this way. So when we're doing physics, we don't really use the tip to tail method other than to make pretty drawings, because we want good numbers. We'll deal with vectors in a more algebraic way, okay? And our algebraic approach is going to depend on the Cartesian coordinate system, which you're all familiar with. It has four quadrants for 2 dimensions and 2 axes. If we go 3D, you would have 3 axes, and you'd have, oh, we don't even want to talk about how many quadrants. Okay, so we're sticking with 2D. When you take statics or dynamics, you'll get into that 3rd dimension. By convention, we may measure angles starting from the plus x-axis. If we were measuring from the y-axis, you'd start with the plus y, but by convention, we usually measure angles from the plus x-axis, okay? The x-axis and the y-axis are always perpendicular to each other. That means that there's 90 degrees between the plus x-axis and the plus y-axis, or the plus y-axis and the minus y-axis, minus x-axis. Now, you know from earlier math classes the following about the quadrants. We number the quadrants going in counterclockwise direction. There's a method to the madness. There's a reason why. It has to do with torque. We'll talk about torque near the end of the semester. So this is the counterclockwise direction. We always start at the plus x-axis is 0, plus y-axis is 90 degrees. The minus x-axis is 180. We get to the minus y-axis, that's 270. And then when we come back around, we've gone a full 360 degrees. Okay? Any vector in the Cartesian coordinate system is thought of as the sum of 2 vectors, one that is parallel to the x-axis and one that is parallel to the y-axis. All right? So, we look at this image. Here's a vector A, and we can think of vector A as its component parallel to the x-axis plus its component parallel to the y-axis. So any vector can be broken down into component vectors. To get the magnitude of these vectors, we use geometry of the right triangle. Okay? Now, if we look at a right triangle here, guys, here's a right triangle. There's our 90-degree angle. Let me make sure that this is showing up on the screen so that you're getting it. Yes, there we go. There's our 90-degree angle. Okay, if this was our angle theta, okay, and this was the plus x-axis, this would be the adjacent, and this would be opposite. Okay? If this was a vector A, AX would equal A, well, the magnitude of AX would be the magnitude of A cosine of the angle theta. So the adjacent goes with cosine. Opposite, the magnitude of AY is equal to the magnitude of A times the sine of the angle theta. opposite. Okay? So you can say opposite is equal to hypotenuse times the sine of the angle theta. Adjacent is equal to hypotenuse times the cosine of the angle theta. Now, guys, if that's not drilled into your head from earlier classes, it needs to become a mantra at this point because we use it a lot. Okay? Adjacent, AX. Notice in the notes here. Okay? AX is equal to A cosine theta. Notice there's no vector signs over the top because these are just magnitudes. AY is equal to A sine of theta, where theta is the angle made with the x-axis or a line parallel to the x-axis. And it can be positive or negative, and all these is allowing us to calculate magnitude. Okay? Magnitude. Now, here's another example of a vector being broken up into x and y components. Okay? Note, if a vector of interest does not have its tail on the origin, it doesn't matter. We can draw in a new xy coordinate system at the tail of that vector. Okay? And as long as the x-axis of our new coordinate system that we drew in is parallel with the old coordinate system, we're just fine. It doesn't matter. Now, let's do some examples of breaking things up into component vectors. Okay? So I'm going to put some vectors on the board over here, and we're going to look at component vectors. Let's say the magnitude of vector A here is 15.0 meters, and this angle is 42.0 degrees. Okay? Make sure that I've got that lined up. Okay, there we go. There's our vector. Okay, so A is 15 meters long, and that angle is 42 degrees. So the magnitude of AX is going to be 15.0 meters times the cosine of 42.0 degrees. So 42 cosine times 15 gives me 11.1 meters. AY is going to be 15 meters sine 42.0 degrees times 15 meters, so I get 10.0 meters. Okay? AX, AY. So any vector you can divide up into x components and y components. Now I'm not going to bore you in a video doing multiples of those. I'm pretty sure you can catch on. Now, remember that physics is very concerned about directionality. Remember that velocity is not only interested in how fast you're going, but it's interested in what direction you're going. So to indicate direction for component vectors, we have what are called unit vectors. The I unit vector, the J unit vector, and the K unit vector. I hat, J hat, K hat. The little hat means unit vector. The I unit vector, okay, is a vector 1 unit long that points in the positive x direction. The J vector is a 1 unit long vector that points in the positive y direction. The K vector is a vector 1 unit long in the positive z direction. Now, right now, we're going to be worried just about I and J. not really worried about K because we're sticking to 2D. Okay, so if I had a vector and it said it was minus 6I, well, I know that vector is along the x-axis because we've got the I unit vector, and the negative out in front of us says that it's pointing in the opposite direction of the I vector, and the 6 says that it's 6 units long. So if I was going to draw that in, I'd start at the origin and draw something 6 units long in the negative x direction. Okay? Now, if I look at a vector broken up into its component vectors, A would equal a vector AX plus a vector AY, and B would equal BX plus BY, then C is the sum of A plus B. I just add AX plus BX times I hat and AY plus BY J hat. So let's scoot on over here. So if vector A was written as 15I minus 6J, and vector B's components were minus 10I plus 12J, then vector C, which was A plus B, would be 15 minus 10 I plus a minus 6 plus 12 J. So 15 minus 10 would be 5I, and minus 6 plus 12 is a plus 6J. So vector C would be 5I, 6J. Okay? 5 units along the plus x-axis plus 6 units along the plus y-axis. And it's straightforward vector addition. Now, remember when we multiply a vector by a scalar, we just change the magnitude. So if I had my vector A is equal to 2I plus 2J, and vector B was equal to 2A, then it would just be 2 times 2I plus 2J, or it would be 4I plus 4J. If I had a vector C that is equal to minus 2A, oh, let's just for fun's sake, let's make it minus 3A, then it would be minus 3 times 2I plus 2J. So I get minus 6I minus 6J. The negative sign changed the direction that our vector point, each one of those unit vectors point. Okay? Now, we want to be able to go back and forth between magnitude angle and component vector form. This is very important for us because we're going to do it quite often. Okay? And to go from component form to angle length form, we again just need to think about our right triangle. Now let me give you kind of the board look and then we'll do some examples. So when I have a vector A and it's got components AX and AY, then the magnitude of A is just the square root of A squared plus B squared. Because remember, for a right triangle, A squared plus B squared equals C squared, where C is the hypotenuse. And the angle theta, which is the angle adjacent to the x-axis, is always equal to the inverse tangent, the magnitude of AY over the magnitude of AX. Now guys, I usually use that as magnitude, and if this were to point in the second quadrant, or the third quadrant or the fourth quadrant, if I just use the magnitude, it's going to tell me the angle to the plus x-axis or the minus x-axis, okay? And from my drawing, I'm going to know what I've got. So let's play a little bit over here. Check and make sure the angle is right. That's where I want us to be looking. Let me scoot this over here a little bit more. Okay. So, let's say I have this, and I've got one vector that's 3 units here and 5 units here. So this is the sum vector. So if this is vector AX and this is vector AY, there's vector A. And this would be my angle theta. So the magnitude of vector A is going to be the square root of 3 squared plus 5 squared. So 3 squared plus 5 squared is 34. Take the square root of that. I get a magnitude of 5.8. I'm going to go with 2 sig figs. I'm making up numbers. To get my angle theta, then I'm just going to take the inverse tangent of AY magnitude, which is 5, over AX, which is 3. 5 divided by 3, inverse tangent, and I get 59 degrees. Okay? Now, if my vector was in another direction, let's say that my AX was a minus 6i, okay? And my AY was a minus 9j. So I'm down here in this quadrant. My angle theta would be this one, okay? So if I want to get the magnitude of this vector, my pink A, it's just going to be square root of 6 squared plus 9 squared square root. So 6 squared plus 9 squared. Take the square root of that, and I get 10.8. And my angle theta, which is now from the minus x-axis, is the inverse tangent of 9 divided by 6. And I get 56 degrees. Okay? So, in a case like this, okay, when you want to indicate where your angle theta is, it's critical that you do a drawing. Without the drawing, the meaning of the angle theta is lost. Okay, so you've always got to do a drawing. So I've got the magnitude and I've got the angle. Now guys, remember, when we're looking at magnitude of a vector, I'll always put it in absolute value signs. Okay, like this was 15 meters. And my angle theta, whatever it is, let's say it was 25 degrees, okay? I always have to have a drawing that shows me where that angle is coming from, because I've got a magnitude and I've got an angle, but I need a little bit more information. I need that Cartesian coordinate system so that I know, ultimately, in that coordinate system, what direction my vector is going to point. So, and a magnitude and an angle are great. We need that information, but without the coordinate system to give us reference, without a drawing to show us where the angle is measured from, it's not all the information we need for a successful ultimate problem solved. Come on, where's the... Okay? Now, just so that we make sure that we understand, Sometimes you might want the angle off the y-axis, okay, the angle phi. And if we want the angle phi, now our adjacent leg of the component vectors is the y-axis. So the magnitude of c sub y is going to be negative, well, c sub y, and they really didn't draw this in. If you drew the vector sign over it, it'd be the negative of the magnitude of vector c times the cosine of phi. Okay? And the x component would be c sine of phi. Now I would probably break this down and do it in 2 points, calculate the magnitudes, and then assign whether it is in the plus I or minus I direction, the plus j, minus j direction. They kind of did it in one fell swoop here. So from here on out, we're going to be breaking vectors up into component vectors on a regular basis. And you need to be really comfortable with this, okay? And this is the last thing on test 1. So with the end of this chapter, we are ending the material for test 1. So math skills, chapter 1 about motion diagrams and the different kinds of graphing techniques we'll use. The one-dimensional motion problems in chapter 2, including free fall and vectors, are all part of test 1. So study hard.